Uh, so we finished yesterday talking about how to construct a confidence interval for a set of data, and we said that a confidence interval, in general terms, is some estimate, some point estimator from the population, whether that's p hat or x bar, plus or minus some margin of error. And we can express that in this way, or we can just give an algebraic interval of a min and a max. And what that does is that gives us an idea, a reasonable or a plausible idea as to where the true population parameter lies. So today, what we're going to do is take a look at what that means in terms of calculating a confidence interval for p hat. So everything we do today will be based on finding a confidence interval for p hat. And so what I need to do is pull up some older notes, and so when we construct a confidence interval from our data, we need something a little more than just this idea of a margin of error. And so the margin of error is broken down into the product of a critical value, which we're going to talk about in just a minute, and simply the standard deviation of the statistic. That standard deviation of the statistic is also known as the standard error. And I'm not going to go into a great deal of explanation, but if you want to read through a couple of pages on your page 486 and 487 of your textbook, it gives you a good explanation or understanding of what this standard error really is all about. But for us, for right now, the standard error is simply the standard deviation of the statistic that we're using. And so for today, we're going to be talking about p hat. Tomorrow, we'll talk about x bar. And so this standard error will be calculated using the population standard deviation and the size of the sample. This critical value then is really what we want to spend a little bit of time talking about. So let's imagine for a minute we want to construct an 80% confidence interval. And so the kind of the derivation of this critical value comes from looking at the table A values for 80% of our data. Remember that our sampling distribution, we're going to assume, or we're going to be able to prove, that the sampling distribution is normally distributed. And so if we want 80% of our data contained within a particular window, then we can think of it as kind of a two-tailed example we've done before, where we're chopping off the left tail and the right tail. If 80% of our data is in the middle, because of symmetry, we know that 10% is in the left-hand tail and 10% is in the right-hand tail. And if we go and look up this value, find a value of 0.1 in table A, we'll see that the Z value corresponding closest to 0.1 in table A is a value of 1.28. So if you just look at the left-hand tail, then Z would be a negative 1.28. If you were interested in the right-hand tail, Z would be a positive 1.28. So this critical value represents that Z-score, or that standardized score, corresponding to the amount of data that's left out of our interval. And since our distribution is symmetric, then we're going to make use of that symmetry and say that half of it is in the left and half of it is in the right. Now, if we knew that our distribution was skewed, then we can still go through this. We can still go through this calculation, but we have to use another type of distribution, which is called the chi-squared distribution. We may or may not get to that before test day, but just have it in your mind that we can answer these questions for a non-normal distribution. But for right now, normal distribution is good enough for us, and so we're going to make use of that symmetry. 80% of our data is contained inside the interval, and so 10% is on either side. That corresponds to a Z value of negative 1.28 or a positive 1.28. And you'll notice that I'm putting an asterisk here to indicate that this really isn't, we're not talking about just the Z value, it's the critical value. And so we're going to take the absolute value of that. We want this product to be a positive number. And so we're going to take the absolute value of that. And because we're taking the absolute value, we're going to call it Z star or Z critical or just the critical value. So Z star is really just the absolute value of the Z value we would look up corresponding to the left and right tail when we're excluding what we want to contain in our confidence interval. And we'll go through another example of this from start to finish, but this is just a good example, and with 80% confidence, we've got plenty in the left and right tail. It's easy to see in the graph here. So how would we kind of frame this question? So we want a one sample Z interval. Now, if we have taken multiple samples, and we have data from those multiple samples, we'll still use this general form, p hat plus or minus a critical value times the standard error here. But we're going to replace the critical value of Z star with a value from a t-table, which we'll talk about later. But for right now, you need to be able to remember, you have to distinguish between a one sample test and a multiple sample test. If all you have is one sample from a population, then you're going to use Z star. If you have more than one, 2, 3, 5, 10, 25 different samples of the same size N, then this critical value will come from another source, and we'll go through that when the time comes. But for right now, we're talking about a one sample Z interval. And so Z critical, or this critical value, comes from table A, and it represents the area between a negative Z star and a positive Z star. And we have to, again, remember to take advantage or to double check that for a sample proportion, we have to double check that our distribution is in fact normally distributed, and that the 10% condition is in place. The third condition that we would have to check is that it's the data comes from a random source. And in this case, we don't have a particular case to look at. But the third thing we would also have to verify is that it is from a random source. So we're gonna start with this general form for a confidence interval where we have expanded the margin of error into the product of some critical value and the standard deviation of the statistic. And in this case, that standard deviation of the statistic is often referred to as the standard error. So let's take a look at an example and see how this would turn out. So we conducted a poll, a singular poll in 2013. So this is a one sample test. All we have is one data from one particular poll. And we found that 52% of US adult Twitter users get some of their news from Twitter. The standard deviation of the proportion, in other words, the standard error, was 2.4%. And we may assume a normal distribution to model the sample proportion. So here we've been given kind of a get out of jail free here. We're told that we can assume the sample proportion is going to be normally distributed. And so from this, we want to construct a 95% confidence interval. Now, a confidence interval means we're going to end up with a min and a max value. So let's take that general form and estimate plus or minus the product of a critical value times the standard error. Well, we've been given the estimate. We found that 52% in the poll, 52% said they get some of their news from Twitter. And so we don't know what the true population parameter is, but we know what p-hat is. And so we're going to take that as our point estimate for the population parameter. The standard error, we were told, is 2.4%. So we'll plug that in. And so now how do we come up with this critical value? Well, we get that from the fact that we want a 95% confidence interval. And since our distribution is normally distributed, 95% of the data is here in the middle. So that gives us 2.5% on each of the tails, or in each of the tails. And so I'll go ahead and pull up table A here for us. I should have pulled it up already, but I didn't. So let me pull up table A real quick. We'll scan through here until we find a value that is close to, let's look at the left-hand tail that we want. So we want 2.5% or 0.025. And we're scrolling down through here and we see that right here we have a value of 0.0256. And here's 0.025, and so we read that value as negative 1.90123456. And so right here well, let me just highlight it. Where are we? Right here, we find 2.5% in the tail. And that corresponds to a z-score of negative 1.96. So we're going to take the absolute value of that and we'll plug that in here as our critical value. So when we do the arithmetic, we come up with an interval of 0.473 to 0.567. And so now to interpret that, we would say something like we are 95% confident that between 47% and 56% of US adult Twitter users get some news from Twitter. We don't know where the true value lies, but based on our one sample, we're 95% confident that it's between 47 and 56%. So that is the simplest of all examples that we can pull out. In just a minute, I'm going to work through a couple of other examples. But before we move on, I want us to think about what we've just done here and answer some true-false questions. So since the standard deviation or the standard error of 2.4%, we conclude that 97.6% of US Twitter users were included in the study. Well, that's false. The standard error has nothing to do with the size or the number of people involved in the study. Let me rephrase that. The standard error doesn't directly talk about the size of the sample. In our second example that I'm going to do for you, there is a way for us to figure, if we know what the margin of error is, we can take this value and calculate an n, but the standard error does not tell us directly the number of people contained in the sample. Question D, if we want to reduce standard error of the estimate, we should collect less data. And the answer to that is false. To decrease standard error, we want to increase the sample size. And so go back and look at this formula here. Standard error is here, and the sample size is in the denominator. So to make this number bigger, to make this number smaller, to reduce the variability in our sample, to make this number smaller, we want to increase this value. So to reduce variability, we always want to increase sample size. And that's true when we're dealing with a distribution of X bar as well. To reduce variation, we always want to increase sample size. And so the last true or false question is, if we construct a 90% confidence interval, this confidence interval will be wider than a corresponding 95% confidence interval. And the answer to that is false also. The lower the confidence, the more narrow the interval. And so you can think about that in terms of looking at this graph here. To reduce the confidence, these tail sections grows. So to go from 95 to 90, I would have 5% here and 5% here. So that would squish in these two bars, and the confidence interval would be more narrow. These values would be closer together at a 90% confidence interval. Okay. So with that, I'll move on. And here I'm going to switch to using the camera, so I can kind of walk through this example step by step. And if you want to turn in your textbook, this example is problem number 8. It's problem number 35 on page 496, but I've got it completely written here. You may want to look at it a little bit later after we're done. But basically, the question is this. In the Harvard School of Public Health, conducted a survey of U.S. college students, and 2,105 of the college students out of 10,904 said that they were abstainers or non-drinkers. Okay, and so from this data, we want to interpret a 95% confidence interval for P. So P is the true value of all U.S. College students. So that's a big population. So before we start constructing the confidence interval, we have to check our three conditions for inference here. And so the first one is the data from a random source, okay? So, well, the case doesn't really say it in black and white, but we are going to be able to trust that the Harvard School of Public Health, this is not their first time to conduct a poll, so we're going to assume that these guys know, well, both of my pens are gone dead. What's going on? We're going to say, my goodness, what? All of my pens are. Okay, folks, we may have to call off class. I'm running out of pens. All right, here we go. So the Harvard School of Public Health knows how to conduct surveys, and so we're going to say that this is a well-conducted random survey, well-conducted survey by the Harvard School of Public Health. So it's from a random source. Okay, so the second question here is it normal? Well, here we have to check whether n times p and n times 1 minus p are both greater than 10. Well, first of all, we're going to have to figure out what p is. We don't know what p is, but we do have an ability to calculate our p hat, which is 2105 divided by 10,904 in this sample. And let's do that calculation real quick. 2105 divided by 10,904 is 0.193. So that's the value we're going to use here. So p hat is 0.193. And that's our point estimate for the true population parameter, and that's as good as we've got. So we're going to use it. So n here is 10,904, and p hat is 0.193. I won't do the arithmetic, but all we need to know is that it's greater than or equal to 10, and we're sure of that. And the same thing here, 10,904 times 1 minus 0.93. Again, we're confident that that's greater than or equal to 10. So from that, we conclude that the sampling distribution of p hat is normally distributed. Is normally distributed. So we've got a good idea of the shape. And then the last thing we need to talk about is the 10% condition. Is the 10% condition met? Is n less than 1/10 the population? Well, the population here is all U.S. college students, and we're pretty sure there's more than 110,000 college students in the U.S. So 10,904 is less than 10%, and we're going to go with that. Heck, there's probably more than 100,000 college students in the state of Kentucky. So we're going to say that these three conditions are met. And so we can go ahead and proceed with our confidence interval. And so the form that we're going to take is we've got an estimate plus or minus some critical value times the standard error or the standard deviation of the statistic. Well, our estimate here is p hat, so that's 0.193, plus or minus our critical value. Well, we want 99% confidence here. So we got to go to table A and see what value corresponds to 99% confidence. That means there's 1% in each tail, or that we're looking for a value here of 0.005. And if we scroll through, we're looking at, here is, so somewhere between this value and this value. Let's highlight this again. So somewhere between those two is 0.005. And so if we read across here, we get negative 2.1234567 or 8. And so here's what most people do. It's in between 2.57 and 2.58. Most people will pick 2.57 as that critical value because it's conservative in our calculation. So let me switch back here to the camera and we'll see what that does for us. So we're going to pick the critical value to be 2.57 times the standard error, which is just the square root of 0.193 times 1 minus 0.193, all divided by the sample size, 10,904. And when we calculate that value, we get an interval of 0.183 to 0.203. So our confidence interval is 0.13 to 2.03 with 99% confidence. Okay. So let's go back to what would happen if we use the other value, 2.58, out of table A for this value. Well, what's going to happen when I multiply these two values together, I'm going to get a slightly larger number here, or this product will be larger, so this one will be slightly smaller, this will be slightly larger. So my interval will be slightly wider than this one. And so this is a more conservative approach. So with a 99% confidence interval, you'll find that most people will use the value of 2.57 instead of 2.58. Although from table A, you could make the case of using 2.58. And after a while, we'll see 99% confidence, 95% confidence. And so these two numbers, 2.57 and 1.96, they'll stick in your head. You'll eventually get to where you don't have to look it up. But in any event, 2.57 is associated with a 95% confidence level. Okay, and so we read a newspaper article that claims 25% of U.S. college students are non-drinkers. Use our result from Part A to comment on this claim. Well, their p hat, wherever they got it, is 0.25. And based on our result here, 0.25 falls outside this interval. And so our comment would be something like this. At the 99% confidence level, it is unlikely The article's claim is true because it is outside our confidence interval. So here I've used the term confidence level and confidence interval in the same sentence. So what do I mean? Remember, a confidence level says that if I were to take this sample over and over and over again, I would expect 95% of the samples that I take of sample size 10,904, essentially using the same method, 99% of those confidence or 99% of those intervals will contain the true population value. And so at the 99% confidence level, I feel good that the true value is between here and here, and 0.25 is well outside this confidence interval. Now, if the newspaper article had said 21% of college students, I would still say it's unlikely because it's outside this interval. But if I reduced my confidence level, then my interval would probably include 21%. But at the 99% confidence level, which is a pretty high degree of confidence, this is something leads us to conclude that this value doesn't make sense based on the sample we did here. Okay, so that's how we can construct a confidence interval from a sample of data. First of all, we're going to check that the conditions of inference are met. We'll use this general form, estimate plus or minus a critical value times the standard error. Critical value is going to come from table A. The standard error is simply the standard deviation of the statistic, and the statistic here is p hat. So we use this form of the equation, and then we simply do the arithmetic here to create the interval. Pretty straightforward. I think the hardest thing that you'll have to get used to is figuring out where this value comes from. And remember, this is a one sample Z interval because we only took one poll. The Harvard School of Public Health conducted a survey. They didn't conduct 10 surveys over a period of a month. They conducted a single survey. So what we have here is a one sample Z interval. If we had data where they had conducted more than one survey, then we'll be able to sharpen the pencil a little bit here. But for right now, all we have is this one sample. And this is the interval that we get from that sample. And if you look at it, it's a pretty small number, between 18% and 20%. So it's a pretty narrow interval. We think we've got it narrowed down pretty well based on this one particular sample. Now, earlier I had mentioned that we can use this method to figure out how big our sample size should be if we want a certain level of confidence or a certain margin of error. And so that's the next example I want us to walk through. And again, this example comes straight out of your textbook. It's number 45 on page 497. And so I show you this because I'm going to do a little bit of arithmetic or algebra. I guess it's a little more than arithmetic. I'm going to do a little bit of algebra here using the relationship that we have for margin of error. And that is in your textbook on, you might want to mark it on page page 493. So you might want to jot that down on your notes, page 493. You want to go look back at that. And let's just start with our example here. We have two candidates running for mayor in a large city. Okay, I'm going to highlight the word large here. That's going to come back and help us in a little bit. And we want to estimate the proportion P of registered voters who plan to vote for one of the candidates, Gloria Chavez, with a 95% confidence and a margin of error no greater than 0.03. So it can be up to 0.03 or less than or equal to 0.03. And so how large of a sample do we need to take? Okay, before we ever start sampling, we don't know how many people to call. And so this is the calculation that the folks at Gallup and all of these other sampling organizations want to do. Before they take a poll, they need to know how many people to call. And this is how they go about it. They say, okay, we can live with a margin of error of 3% or 5% or 1%, whatever that number is. They decide what the margin of error is going to be, and they want it no greater than 0.03. So we want the margin of error to be less than or equal to 0.03. Well, what is our margin of error? Well, it's this, since we're doing just one survey, it is Z star times the square root of p hat times 1 minus p hat all over n. And n is what we're looking for. We want that sample size. So I can see your eyes starting to glaze over here. Oh, this is algebra 1 or algebra 2. We've got to rearrange this inequality and solve for n. So let me do a few steps of the algebra here. I'm trying to isolate n, so I'm going to just divide both sides by the square, or the side by z star. So I'll get the square root of p hat times 1 minus p hat over n is less than or equal to 0.03 over z star. To get rid of this radical here, I'm gonna square both sides. So when I do that, I get p hat times 1 minus p hat all over n is less than or equal to this guy squared. Okay. And so now I'm still wanting to solve for n, and this is kind of like a proportion here. So I'm gonna kind of cross multiply, but I want to get n over here by itself. So I'm going to multiply both sides by n. So I get n on this side, and I'm going to divide by this whole thing. So I'm just going to kind of switch places. And when I do that, I end up with z star over 0.03 squared times p hat times 1 minus p hat. Okay, and so I know that z star comes from this 95% confidence interval, and we looked it up already, and this value here is going to be 1.96. So this thing is just going to be a number. It's 1.96 divided by that squared, whatever that turns out to be, and it's times this thing right here. Well, if I knew p hat, then I could solve this inequality and I would know what n is. But the only way to figure out what p hat is to conduct the survey. And I can't conduct the survey until I know how many people there are. So I'm kind of caught here between the hammer and the anvil. I need to find N, but in order to find N, I've got to have P hat. In order to get P hat, I have to have N. So I'm kind of caught in the middle. So what do I do here? Well, what I'm going to do is I'm going to recognize that I want to make sure that I get the largest sample I can possibly get, right? Remember, more samples is better. More people in the sample is better. So I want this product, P hat times 1 minus P hat, to be the largest possible value I can be. And so over here on the side, I can do a couple of calculations. Let's say that P hat is 10%. So that's 0.1 times 0.9. Okay, and if I multiply those two things together, I get a value of 0.09. Okay, so let's say that this is 0.2, and so this one will be 0.8, and I'll get a value of 0.16. So as I do that, I notice that as I increase this value, as I increase P hat, the product gets bigger and bigger. And if you keep going down through here, what you'll see is to maximize this product, I need to use a P hat of 0.5 times 0.5. If I use 0.6 and 0.4, then it starts to go back down again. And so to maximize this product, I'm going to use 0.5 times 0.5. So when you're calculating the sample size that you should use for your survey, you don't know P hat. So what you want to do is make sure your survey is as large as it could possibly be. So we're just going to use 0.5 times 0.5 here. So we'll take 1.96 squared over 0.03 squared times 0.5 times 0.5. When you do all of that arithmetic, I think you end up with N has to be greater than or equal to, I think it's 1,067 something. So we're going to round it up to, we're always going to round up to the next whole number. So I think this turns out to be 1,067.1 or something like that. But we're going to round up to the next whole number because, like I said, we want to make sure N is as large as it can be and still meet what we want to have in terms of the level of confidence and the margin of error. I mean, I could make this number 20,000. But to sample, if I only need to sample 1,068 people, why would I want to go to the cost and time of sampling 20,000? So 1,068 will give me 95% confidence and a margin of error no more than 0.03. And so, I mean, this number seems very, very reasonable based on what we read from our Gallup poll methodology. If you remember, they were sampling, adults in the U.S., population of, I don't know, 200 million adults, something like that. And those sample sizes would typically end up being somewhere between 1,000 and 2,000. So you can see here, if I want higher confidence, if I wanted 99% confidence, I would plug in 2.57 here. And so this number is going to get larger. Margin of error is going to stay the same. I'm still going to assume P hat to be at its maximum value. So all I have to do is replace 2.57 here, recalculate that, and I get a new value for N at 95% confidence. Or if I wanted to change the margin of error, then I could substitute in 0.02, or maybe margin of error of 0.05 is okay. We can see how that affects what we want to do. So here are two examples of using confidence intervals and how we might do that in calculations. And so let me get back to the screen here. There we go. And so we've been at this a pretty good while. So these are two really typical examples of how we might work on confidence intervals using a population proportion. And so for tomorrow, what I want you to do is just take the two problems right after these two, 836 and 846. Okay, that basically it's the same process as what we went through. The numbers are a little bit different. The case is a little bit different. But you should be able to kind of go through the same process that we've been through here and come up with a confidence interval for teens who have an online profile on Facebook. So this will tell you how old the textbook is. There's no mention of Snapagram or TikTok or any of that other stuff. So and then question 46 is what sample size is required to get a 90% confidence level with a margin of error of 0.04. And so it's basically the same thing as what you've done here, or what we did here, and should be pretty straightforward. But these are typical calculations involving confidence intervals. So I'll stop here. I'll ask, does anybody have any questions? Nobody sang out while I was talking, and I know I talk fast. I wanted to get through both of these examples. So on Friday, my plan is to take your questions if you have any questions on what we've talked about this whole week, because we're really drinking water out of a fire hose here. We're trying to get through a lot in a short period, but I think these two examples that I've given you are going to cover most of what you'll be asked to do on an open response question in the AP exam. So any questions here? All right. Well, guys, keep plugging away. And I hope everybody's doing well. I'm glad to see you guys being faithful. I do know that several people are watching this after the fact. I don't know if it's work schedule or if the weather's just too nice and they don't want to be inside right now. I don't know, but I do know many of your classmates are checking this out on YouTube. And so, but I am glad you guys are able to join me, and I'm grateful for that. And so with that, we'll see you tomorrow, same time, same place. Y'all have a good afternoon.